Hello, and welcome to part 2 of my Getting Started with Carbon guide. If you haven't had a chance to check out the first part in this series yet, I definitely recommend that you jump back and give that a watch before heading into this one. In this video, I'm hoping to expand a little on some of the concepts which we discussed in the last part, and hopefully give you a sense for how you might start to go about expanding your experimentations into actually starting to put together something resembling an actual game. In this video, I will be building a project that has some gameplay elements in it. It won't be a full-blown game. In the short time that I have available, I don't think that's going to be possible, but hopefully it will introduce you to all of the concepts that are generally necessary in order to start to achieve that. So some of the things that I want to talk about are primarily application states, which is effectively a concept that allows us to customize how our game plays out. Our application might be in various different states throughout its life. For instance, we might be in a main menu, or we might be playing the game, a high score table, that kind of thing. That's what application states are for. We'll look at those in more detail in just a little while. I would also like to look at construct scenes and spawning objects. Obviously, it's not always going to be possible for us to create and embed every object that we will ever need in the scene itself, that will be loaded as the scene loads. Sometimes we're going to want to create objects or design them elsewhere and then load them dynamically at runtime. We don't necessarily want to have every character we need all standing in a room in our main scene just so that we can reference them. So construct scenes and spawning objects, that's a way for us to achieve that. We'll look at that. I would also like to touch upon script communication. In the simple script that we designed in the last video, it was very self-contained in the sense that we just had one script and it handled everything. In a larger project, you're going to need scripts to communicate with one another. It becomes important in a larger project to be able to abstract your script classes or your individual pieces of more complex objects. So we'll look at that too. And if I get a chance, I also would like to look at a couple of other object types, possibly particles and actors, so that we can see some animation, and also possibly environment navigation, setting up environment navigation and doing some simple agent behaviors to navigate our scene. So that's the general plan, and so without further ado, let's jump straight in. You'll notice the scene that I have open at the moment is the scene that I was working on towards the end of the last video, where I imported this vehicle here, this Viper, and we assigned a simple object behavior to it that allowed me with the keyboard to rotate the turret and fire massive projectiles. It also allowed us to rotate the wheels. Now, for the most part, this scene is as it was when we left it. I have made a couple of modifications. If you recall, when I first imported this vehicle, I scaled it up and then instantly regretted it. It was way too big. So I fixed that. I've scaled it down a little bit. I've also tweaked some of the materials so that it looks a little bit nicer. I added a half-strength environment map, edited the metalness. I also adjusted the Fresnel term, just to make it a little bit, a little bit more, have a little bit more pizzazz to it. Other than that, it is exactly as we left it. The vehicle still has its behavior script executing every frame, which is this one here, viper.js under scripts, which, if you recall, we basically hooked into the update process to read the state of the keyboard and to rotate the turret and the wheels and fire. Here we created an entirely brand new mesh and fired it into the scene to do whatever it would. So a little bit later in this video I will be returning to this scene and we will start expanding it a little bit more. But for right now I'm going to create a new scene so that we can take a look at setting up a navigation mesh and playing around a little bit with the navigation controls so that we can, you know, get a little bit of movement in our scenes. So let me do that. I'm actually going to close this scene and I'm going to create a new one. Call this navigation. Whoa. Navigation test. Standard scene is fine. And we'll hit next. Finish. Okay, let's delete these guys first of all. We don't need these. Now I'm going to import a scene that I already have. It's the sponsor scene, which is available in the public domain. It's a slightly cut down version of it. Okay, so I'm going to import that guy. Would you like to import to this scene? Yes, I would. Just meshes, there are no other objects in it. Wait for it to complete. Okay. Now before I do anything, whilst everything is selected, by default when you import objects, they don't have a physics model assigned. So you can see model is set to none. I'm going to change that real quick to collision only so that we can stand on it, otherwise we're going to immediately fall through the floor. Now the scene is a bit dark right now. I need to light it up. I already have the default light, which is somewhere. I'll just grab that from the scene outline. And let's move that into the middle. There we go, a little bit brighter there. Actually what I'm going to do is I'm going to move it up, like so. So we get light everywhere. Move it over a little bit so we get an overhang. Okay, then I'm going to get some ambient on the go. There we go. Just so that we get some light in the areas it doesn't touch. Same for the far ambient. Okay, so we get light in these areas as well, which would otherwise be completely black because of the shadow. Okay, I'm going to boost the specular intensity up a little bit because I like these bricks to be a little bit more reflective. Let's boost that up a bit. Let's pick these bricks and we'll pump up the gloss level on them. Same for these guys. Possibly also these pillars. No, that's way too high. 20, there we go. Okay, that'll do for the moment. Okay, you can see that we have a nice sheen to these bricks. They don't look too shiny, but they have a nice kind of bright sheen to them. What I'm also going to do is I'm going to add a skybox really quick. And we saw that in the last video, so I'm just going to click sky. Yes, I would like to add a sky. It's black because it doesn't have a texture yet, so I select it from the World Explorer, from the scene element list, choose the texture. I'm going to choose the one that we built in the last video. And then I'm going to boost its intensity up. Something like that should do. Okay, I'm happy with that. Maybe a tad darker. save just in case. Okay, so the scene is mostly set up at the moment. If I hit F5 to run a preview, hopefully, there we go. The scale is just about right already, but we can walk around this. If we hadn't set the physics model to collision only, we would have fallen through the floor, as I mentioned. Okay, so as I mentioned, what I want to demonstrate first is setting up navigation properties for a scene and having an object navigate around it. Now, the first thing that we need to do in order for that to happen is to add or to generate a navigation mesh for our scene. Now, a navigation mesh is essentially a piece of geometry that is used by the navigation system to understand where to place objects, to give it a surface along which it can find a path. Now, Carbon has a navigation mesh generation system built in, so thankfully that process is relatively painless. Now, in order to add a navigation mesh to our scene, it is a scene element similar to the sky, and you can see it over here on the right. If I click that and choose yes, we should automatically get a navigation mesh generated using the default parameters. Now, this red alpha blended surface designates the navigation area, the navigable area of the scene that has been determined by the navigation mesh generator. Essentially, it tries to work out every surface that is walkable and that an agent can move along. And you'll notice that up here we should have navigation mesh surfaces generated up here too, which we do, which is great. We may even get them on the roof, which we do. So essentially the navigation mesh generator will find any surface that can support an agent or a character, and it will generate these surfaces that we see here in red to denote where it could possibly walk. We won't necessarily spawn characters on them, and since there's no path between this navigation mesh and the one above, for instance, there is no way, if we have a character down here, for that character to ever get up here based on this geometry. But if we were to have a set of stairs or ramps or so on, then the navigation mesh generator would automatically connect those guys. Now, that's the navigation mesh effectively generated. If we click on navigation mesh, you'll see that here are the parameters. If you don't want to see, once you've set it up, if you don't want to see the in-your-face red surfaces, you can select it and untick enable preview. That'll turn that off. That information is saved as well. So also, if you wonder where your navigation mesh has gone, it might be because enable preview has been turned off. So that's something to double check. But we can set up various properties for this navigation mesh. Probably the most important is going to be agent radius, and that defines the amount of space that we want to leave between the edge of the generated navigation mesh and any non-supporting geometry. So here we have these walls, they can't support us, we obviously can't walk along them. So we've said we want to leave 0.6 meters radius wherever possible from a surface. You can see here we have these 1 meter boundaries. This is it is going to generate relatively low resolution geometry, so it's not always going to be exactly what's specified there, but it's effectively the minimum. We never want to get closer to a surface than 0.6 meters. And you can change that. If I were to change that to 0.2, the mesh should be regenerated, and you should see, should see that it's now much closer fit to the edges of the walls, and that looks about right, 0.2 meters ish. So if I change that back, you might want to go much larger. Let's change that to 1 meter. Okay, now we're trying to guarantee that we're 1 meter away at all stages, and go a bit further, 2. and now this navigation mesh has entirely disappeared. Now that's because there's not enough room in the middle to support a character if it's must be 2 meters away from any non-walkable surface. So let's change this back to 0.6. Now, why would you want to configure an agent radius? The main reason for that is to take into consideration the size of the agent's geometry. In this particular instance, we're assuming that the geometry itself of any character is 0.6 meters in radius, so 1.2 meters in diameter. And that ensures that as he comes round the corner and starts to walk up here, up the path here, he's not going to clip into this geometry. He's always going to, even if he was right at the edge of his path, the closest he's ever going to get is 0.6 meters away. So that means his arm isn't going to clip through the wall as he turns the corner. He's not going to try and cut right round very close. Although we could if we set that very small. Actually, that's 0.1. Okay, so yeah, you can see that it's now very, very close to the wall. Taking into account the radius of the agent's geometry, so his mesh, you can see that if he were to take a path right along the edge of the navigation mesh, he's just going to clip straight through this wall. You know, his arm's going to slice through it. It's going to look really ugly. So for that reason, it's generally a good idea to define a radius to keep them away as much as possible. The next parameter is agent height. Now the generally accepted average height for a humanoid male, in games at least, is roughly 1.8 meters. There's plenty of room here. If we look at it from the side on, there's plenty of room here. 1.8 meters is roughly here, so any average sized character should have no problem whatsoever fitting under this archway. But if we change that to something crazy like 5 meters, meaning we expect that the agent that is using this navigation mesh to be 5 meters tall, if we change that to 5, then you'll notice that the mesh, the navigation mesh over here disappears, as it does over here and all around here. I would expect on the second floor for that to go as well, which it is. And the one on the roof should still be here because there's a million miles of headroom there, so that's not a problem. But yeah, we're saying we expect the agent to be 5 meters tall, so he's not going to fit down any of these corridors. So there's no navigation mesh generated there. So if we change that back to 1.8, maximum slope, if you have sloped geometry, that describes how sloped the geometry can be before it will no longer navigate. Maximum step height is how tall a ledge the agent can possibly step up in order to continue navigating. Let me just demonstrate that really quick. If I create this and let's make it quite tall. So let's try 0.5. No, that's still too low. So this ledge that's in the way is taller than 0.5 meters. So the navigation mesh stops, and again it's trying to maintain 0.6 meters at least away from the edge. Let's try 0.8. It's bigger than 0.8. 1 meter, 1.2. There we go. So the path is now no longer interrupted. Now you'll notice that the navigation mesh looks a bit, let's say, janky. It's a bit messed up, but that's actually not a problem. The navigation mesh is a low polygon representation of a path. As long as there is a connection, that's fine. When we process the agent, it's our responsibility to actually plant it onto a surface. This just tells us that there is a path available, so that's fine. You'll notice that the mesh doesn't sit on the surface anyway, it floats above it. Excuse me. So that's okay. So let me just remove that again. So yeah, that means that with those settings, the agent will step over that block because he is allowed to step over at ledges that are at least 1.2 meters tall. 0.4 is 0.4 is generally a good height to go for. So we'll leave that as the default. So we actually have a navigation mesh in the scene now. Let's see how we use it. So the first thing I'm going to do is I'm going to create a cylinder to represent our character. Nothing fancy, no expense spared here. Let me just put him down on the ground. That's fine. Okay, now I'm going to give him a script. I'm going to call this navtest.js. Oh, it would help if I actually created a new one, new text document. Navtest.js. Okay, so I need to open that guy up. He should be in our Asset Explorer, which he is. Okay, so as before, we need to create a new behavior. Class navtest iScripted object behavior. I'm going to want to store a reference to that guy, object node, and node. Our same standard boilerplate for object behaviors. If I'd had more forethought, I would have created a template text file and simply copy and pasted it, but it helps get into practice these in the early stages, the typing out the boilerplate. So we've got a reference to our node. Now what I want to do is I want to enable this node as a navigation agent. Similar to the physics properties, it is actually possible to enable any node to be a navigation agent. It provides essentially default behaviors for navigation. There are other ways, just as with the physics, there are other ways to associate physics behaviors with objects. Similarly, there is also different ways to associate navigation behaviors. But here we're just going to use the default ones that are built in for the moment. So to do that, let's take a look at our reference documentation. Now I want the object node to be able to navigate, and to do that, if we scroll down here a bit, let me just find it. So you can see we've got a number of things to do with navigation here. We've got here's the actual function we need: enable navigation. We also have navigate to, which allows us to specify a position, determine whether navigation is currently enabled. We can get the current state of the navigation. For instance, is it waiting or is it traversing, and so on. So let's just enable it and we'll actually see what it does. So enable navigation expects us to pass in a navigation agent create params. Now again, remember, because it's a script, we omit the CG prefix and we don't have to worry about pointers. This is the C++ reference manual. So we can just go ahead and build a navigation agent create params. Navigation agent create params, and this specifies obviously the parameters excuse me, that we want for the navigation agent that is going to be associated with this this object node. And if we look at those, you can see we've got similar things that we saw when we were building the navigation mesh. We've got the radius, height, we've also got a slowdown radius, which we can go into more detail perhaps later in a later video, but there are various different things that we can specify: maximum speed, maximum separation. There are defaults for these, which is what I'm going to use here. So all we need to do is pass in this this structure as is to use the defaults. So we just do enable navigation and we pass in our parameters. Now if I save that, reloading script, no errors, and if I run, nothing should happen initially, but we get no errors, so that's always a good sign. Now, something I forgot to do, and you'll notice that because this navigation mesh is now broken. Now the reason for that is that when I created the cylinder, I did not change its model from collision only, which is the default for primitives created through the object browser. Subsequently, when the scene was reloaded, it regenerated the navigation mesh and assumed that this was a piece of impassable geometry. So what I actually want to do for this guy right now, at least, is I'm just going to change that to none. And if I force it to reload, you'll see that the navigation mesh has been regenerated correctly. Okay, so what we want to happen now is we actually want him to navigate. Now the way that we can do that is, so we'll override, we'll hook in, so to speak, into the on-key pressed handler, as we did in our prior video, and that's key code uint modifiers. So if key code is, let's say, B, let's reuse B, keys B, then what I want to do is I want the agent to navigate to a position nearby, near to me. Now we saw that we have a method as part of the object node called navigate2, navigate2, there we go, navigate2, that expects a position. And when navigation is enabled for this node, use this method to request the object to autonomously navigate to the specified world space position if possible. Now obviously the if possible gives us a clue that it isn't necessarily going to be able to navigate to us, and we'll see that in a moment. But so we want to call the navigate to, and we pass in a world space position. But what world space position can we use? Well, since we want it in this simple test case to navigate to a point close to me, the player, one way that we can do that is to grab the camera from the scene. So as we saw last time, we can grab the scene from the node, node got get scene, and we should be able to get the currently active camera from the scene itself, get active camera. Now I realized I didn't show you the documentation for that, so let me just quickly CG scene, get active camera, here we go, get active camera. So it simply returns the camera node, a reference to the camera node that is currently the active camera for the scene, and we should just be able to use that as is. So the camera node, which is obviously the object through which we're currently viewing the scene when we're in our preview, that will be somewhere above the ground when we, if I save and we run again, obviously I'm some distance above the ground, roughly 1.7 meters or so, I would say, 1.6, 1.7 meters at eye level for average human height. Now, the navigate behaviors, navigate methods require us to specify a position that is reasonably close to a navigation point, the actual navigation surface itself. So that's close to our feet. So what I'm going to want to do is get the position, so I want to vector 3 navigate point equals camera get position. I'm going to want to offset it down by some amount so that it's close to our feet. Like I said, probably around about 1.6 meters. Now that gives us a good point to pass to the navigation system. It doesn't have to be precise. It's worth pointing that out, that the point that we specified doesn't have to be bang on the surface. It simply has to be nearby. What will happen when you request a navigation is it will search around the point that you specify for a point on a navigation mesh surface to which it will attempt to navigate. So we don't have to be precise, we just have to, you know, roughly approximate a point close to the surface. So I can then request that the node navigates to this point. As we saw, this just expects us to pass a position. Navigate to navigation point. That should be it. Error. Navigation. Oh, it's navigate point. My bad. Okay, no errors. Right, let's see what happens. I should be able to press B, and then this thing flies towards the point where I press B. Okay, let's run over here. Let's see if we can trick it. Hello? Nope. Okay, let's see if I can get it to come down the corridor. There he is. Oh. There he goes down the corridor. So we could change some of its properties. We saw that the navigation creation parameters allow us to specify things like maximum acceleration and maximum speed. How about if we go up onto the second level? I don't know whether I'm going to be able to see him or not, but I can press B to ask him to navigate. I'm not going to be able to see him. Can't see him from here. No, he's obviously down there freaking out that he can't find a path. Let's stand here, see if we can get this to work. Okay, so he's navigated there. If I drop down, but he's just stopped. He's just stopped there because he can't find a path. Okay, now the one issue with these basic navigation tools is, as mentioned, it's designed primarily for finding paths along the navigation surface. Now, as we saw, the navigation surface isn't necessarily tight-fitting to the geometry itself. It doesn't necessarily sit flush. In fact, we can probably see here that this cylinder is... Oops. What happens when you try and press a shortcut key? This cylinder is hovering above the ground slightly. Now, if we go back here, the reason for that is that so does our navigation mesh. It is floating above the surface slightly. Now, there are a number of ways we could correct that. We could, you know, manually adjust the object after it had navigated. So perhaps in our onUpdate method, we could shunt it down onto the ground. But there is, as I mentioned, a number of ways to get navigation behaviors. This is a very, very rudimentary one, where we just assign some parameters to any random node. That could be a light source or anything, and we can trigger it to move with navigate to. One other approach is to use the built-in character controller that's built into Carbon that comes with it. And the way that we do that, if we look at let's go and find the character controller. CG character controller. There we go, character controller. So the character controller is a fairly fleshed out controller class, which I'll talk about more in just a second, that provides both player controlled and non-player controlled movement through a scene. So when we hit F5 and our character is moving around here, and we can walk up to walls and collide with them, and we slide and so on, that is actually a character controller that that Carbon Forge has created for us to use in the preview. So that's an example of a player-controlled character controller. But it also has an NPC mode, a non-player controlled mode, which you can see that we can specify via the constructor for the character controller class. We specify a physics world so that it knows, so that it has access to all the representation of our world in its physical form, and we specify whether or not it's player controlled. Now, also, you'll notice that the character controller has a number of other methods for setting maximum slope, similar properties that we saw with the navigation creation parameters, navigation agent creation parameters. We can set height, radius, offset, slopes. There's functionality for flying, although that's for player controlled. Acceleration, gravity, masses, and so on. But we also have these for when it's in NPC mode. We have navigation functionality similar to that which we saw in the object node. Now the key difference in this case is that the character controller always tries to keep the character, or whichever node it's been associated with, it always tries to keep it on the ground. Now that's completely automatic in both the player's case and in NPC's case. Irrespective of the navigation mesh surface, it will always plant the character directly on the ground. So this is ideal. It's essentially done for us in that instance, so we can just use that. Now the object node and the character controller, is actually a physics controller. It is derived from CG Physics Controller. Now we haven't seen those yet, but a physics controller is essentially somewhat like an object behavior in the sense that it is something which we can attach to object nodes that control its physics behavior rather than its scene behavior. In this particular instance, the character controller handles what we see when we preview for the main player, as I mentioned earlier, and we can attach it to an object node via, if I go to object node, set physics controller, if I can just find that so you can take a look at it. Set physics controller, here we go. Okay, so we can set the physics controller for an existing object node using its set physics controller method. So it should be pretty straightforward to do this. All we need to do, and again we're going to use the defaults here, but all we should need to do is to create a new character controller. Character controller equals. Now in AngelScript, when we're creating a reference object, which this is, we don't use new or GC new or anything like that as we would in C++ or C# or C++ CLI. We just essentially construct it, as I'm doing here. Now, as we know, the constructor accepts two parameters. The first is the physics world, which we need to get from the scene. Which we can get from the node. Get scene. And the scene has a function called getPhysicsWorld. Scene. So many classes. There we go. So scene. Somewhere in here. Let's do it alphabetically. GetPhysicsWorld. There we go. So getPhysicsWorld retrieves the scene's internal physics simulation world. So we can get that from the scene. Character controller scene getPhysicsWorld. And the second parameter is whether or not it was player controlled, which in this case we want to be false. Now we'll get rid of this old navigation stuff. Actually, you know what? I'm going to store a reference to this so that we have it in the key press case. So mController, we'll make that a member variable, and then we just do mController equals. So we've got a new character controller. We're going to attach it to the node. So that way, all we need to do now is call its controller navigate to navigate point. Save that, no errors, and if we run, we should apparently. Oh, I forgot. Controllers have to be initialized. Initialize. So if we go to choose the search. Physics controller, initialize. Now the controller's initialized, called after setting up. So effectively what we do is we create the controller, assign it to the node, we would then set it up. So for instance we would set the maximum agent height or its radius, that kind of thing. Then we would initialize it. We're going to use the defaults for the character controller, so we just want to call its initialize method. Now hopefully when I press B it should navigate. There we go. The defaults for the character controller are much faster. Will accelerate and decelerate much more quickly, and it moves much more quickly as well. It moves at run speed by default. You can change those behaviors, of course. But one thing to notice is that it is sitting flush on the surface there, which is ideal, which is exactly what we want. So with this guy, with the actual character controller, just as it does with human controlled character, it will always keep it sitting flush on the floor. And that's it. That's really the basics of environment navigation. We've created a navigation mesh which has been formed to the scene, and we've seen how we can enable simple navigation, which is primarily useful if we're going to handle all the secondary details of navigation ourselves. Like if we wanted to plant one way or another, we're going to need to plant the object on the ground or do something with it when we're using a navigation mesh, because the navigation mesh is a low polygon representation of the navigable area. But if we're happy that this is going to be like a standard character type, then we can use the character controller, which already provides most of that functionality for us. If you're going to do it yourself, then you can use the standard object nodes navigation behavior, and then you can take it from there, whichever. Essentially that one is the much lower level one, which the character controller itself sits on top of, essentially. So that's navigation. You should now be able to have characters, or objects at least at this point, move around the scene. Obviously you don't have to have it always come towards the character when you press B. You can have it go anywhere. You can pick a point in the scene at random or lay out dummy objects. In fact, we actually have a navigation, we actually have a patrol point type object, which is literally just a simple point, effectively. You can place these in the scene at points, and if you you have its ID, or you give it a name which you can recognize, you can retrieve it later, so that you can go to a known point. Maybe this is a spawn point, or so on. But those can be retrieved from the scene so that you can navigate to a known position if you need to, an objective or so on. You could even consider categorizing these things, so you could find a point which is classified as cover. In fact, I'll show you something which you can do here. For instance, let's say we wanted this to be in cover. Now, one thing that all objects have are these custom properties here. None are defined. If I click the browse button there next to custom properties, I can actually add some custom properties to this guy. And it is essentially a name type value concept. They're completely custom. So I could call this is cover, set that to a ball, and set that to true. And you can see we've got one property, is cover, ball is property, its value is 1. And I could set that differently for this guy who's out in the open. Is cover ball value false. So you can see this guy has one property is cover. Oh, did I not set that correctly? My bad. That should just be a number. 0. There we go. So that's is cover 0. That's is cover 1. Now, in our scripts, when we're enumerating these guys, one thing that we have access to in the object node class, if I go to that CG object node, are these functions here. We have get custom properties to get the full container, or we just have get custom property name, because I have get custom property and default value. So in our script, when we're enumerating those, we can actually get the custom property from it. So if we got our list of patrol points, we could do patrol point dot get custom property is cover, and in this case we want a default. We'll assume that if nothing was provided, we'll just assume it's false. Is cover equals. So we could get it from the node itself. We could define those there. Whoops, I capitalized the I there. So we can communicate things that way to our scripts as well. And in this particular instance, rather than always when we press B move towards the camera or the player, we could enumerate nearby patrol points. If we want to get in cover, we could find nearby patrol points that have their is cover set to true. If we weren't in a particularly alert state and we didn't care about cover, then we could find any old point that we needed. So that's navigation. I'm going to leave that there for now. At least that's the fundamental principles of navigation. And we're going to move on. So let me close this guy down. And that one. Let's get rid of this test line. Save. Okay, so moving on. What we're going to look at now is the concept of construct scenes and spawning objects in at runtime, something which will become increasingly important as you start to build your games. So for that, I'm going to go back to our sample scene, rather, with the Viper. Now to demonstrate this, what I'm going to do is I'm going to modify this code, this behavior rather, the Viper, which at the moment when we press the B key we fire a projectile which we create procedurally on the fly. Here we create a sphere mesh, attach it to an object, change its material, and then we set its physics model and so on. That's going to get very, very tedious if you wanted to do that for everything. You would have to write all the code out every time you wanted to create an object, and obviously it's not always possible to create something procedurally through these simple creation functions which are available. So what we're going to do is we're actually going to design a projectile elsewhere, and then when we press B we'll simply spawn it rather than going through this manual creation process. Now to do that, as I said, when the main benefit of the construct scenes is that it is a place to design prefab objects that you can't have in the scene when it first loads. Obviously something like a projectile, we couldn't really have that be in our scene to begin with. And again, I know that we are saying projectile here, but it really is just a sphere. but we'll expand on that a little bit as we move forward in this explanation. So what I'm going to do first and foremost is to create a new scene, and we do that the same way we did before. We go through the wizard. I'm going to call this construct test, and we're going to call this, we're going to set the type to construct. Again, these defaults are all fine, so we just hit next, we hit finish. Let's close this guy down for a moment. Now with a construct scene, when we first create it, unlike the standard scene type, we don't get any default objects, so we don't get the default platform with the spheres on it or anything like that. It's just a completely empty scene. One other key important factor to remember is that there is also no default light. So when you first create something, it's likely that it's going to show up completely black. So the first thing I'm going to do is add a light, just so that I can see. The beauty of a construct scene is you can do anything with it. You can have thousands of objects in it, and anything you want, even if you're only going to load one object from it at runtime. So this light is just here for my benefit, so that I can actually see. Okay, so we're going to do pretty much the same thing we did before, procedurally, but this time I'm going to do it manually. Now I'm going to create a sphere at the origin. That might be a bit small, so I'm going to scale it up. Okay, that's fine. And I'm going to create a material for it. Standard material. And I know, let's make it an emissive orange color. Let's make it bright as anything. Similar to the star, the sun, which we'll see a little bit later on. I can boost this HDR, the high dynamic range emissive value, up to make it glow very brightly. So let's assign that. Now, it won't necessarily look very bright as it stands right now because it's the only object in the scene. Let me add a backdrop to that so we can see it in reality. Let's make it a bit brighter. What I'm going to do, I'm going to add a sky element just so that I can get a general tone for the background. The thing with HDR is it's adaptive. It adapts to the environment that you've set up. So in a construct scene you can play around. Again, the beauty of construct scenes, you can play around with things like the backgrounds and so on to see how it reacts. We're not going to load all that stuff at runtime. We're literally just going to pull a certain object. So let me just load the night sky up. So I might even want to go brighter. I'm going to go crazy and set that to 200. We'll show you how that works in practice, but that'll do for the moment. I'm not going to do anything more with that. That will work. So as you can see, I'm in this construct scene, and in fact if I go over here, you'll see I have both scenes open. Now what I want to do is I want this thing to fire from the turret rather than this procedural sphere which we're creating currently. Now the way that I do that is if I open up the Viper's script. Right, let's put this over here for the moment. Right now we get the scene, and then we call the scene's create object node function to create a new mesh node. I'm going to comment all of that out for the moment. And then what we're going to do is, let's go to our documentation and go to our scene class. Now remember, the scene class is where we do most of the work with introducing nodes into the scene, creating them, loading them, unloading them, and so on. Now when we're spawning objects in at runtime, we want to use the load object node function, which is this guy here. Now, even though it lives in another scene, we can still load it from our main scene, the scene that we're working with at the moment, and accepts 3 parameters, at least this overload of it, accepts 3 parameters: the reference ID of the node that we want to load, the method that we want to use to clone it if necessary, and then another ball which specifies whether we also want to load its children. Now we'll see why this is particularly important in just a moment, but for the moment let's fill these 2 out. The reference ID, as we saw in one of our earlier examples, is a unique identifier that is given to every object in the world, in every scene. It is unique for the lifetime of the project, of the world database that we've created. This guy here, if we go over to its properties, has a reference ID of 485, and I can click there and hit Control-C to copy that to my clipboard. And that is, like I say, it's permanent, permanently set to that value, no matter what we do, whether we load or save or move it. The only time it would ever not have that reference ID is if we deleted it completely. So that stays with it forever, so we can be sure that we can reference it in scripts. We might create a define for it and call it, my projectile. But here I'm just going to reference it directly. So going back to our documentation, that's the reference ID that we want to specify. We want to load that object node. The second parameter is actually fairly important for 2 key reasons. The first is for instancing where we want to save memory. So if we want to instance the object that we're loading many times, we don't necessarily want to have hundreds of copies of the mesh, for instance. The actual, in this case it's a sphere, we don't want hundreds of copies of the mesh resident in memory. And if we go into the clone method, you'll see that we actually get a couple of choices for what we can specify for the clone method. This one, copy, will do exactly that. It will make a full-blown copy every time it loads. So if we were to load this thing 100 times, there will be 100 brand new copies of this thing resident in memory, including all of its child resources, excluding textures, I should say, textures and materials. So if this were a mesh, as it is here, we would get 100 copies of the mesh and the physical mesh data. The second one, object instance, will not duplicate the mesh. It will instead reference the underlying object, and we'll see what that means in just a moment. The third option is the data instance, and that will effectively make a copy of the object, but it will reference the same mesh data. That's going to sound confusing for the moment, but we'll see what all that means a little bit later. For now, we'll just know that we want to choose object instance in this particular case, which means that we're not going to end up duplicating any information pretty much at all. So that was the second parameter, and the third parameter is whether or not we want to load children. We'll just leave that at true for now. The object we're loading has no children, so it won't do anything, but in a moment we'll play around with that, and that will be what we need to do. So this is just going to be a regular object node. We don't necessarily care about its type here, and we don't care, for instance, that it's a mesh, because we're not procedurally creating it. So we'll call this projectile equals scene load object node. First parameter is reference ID, which is still in my clipboard, 485, and we want to choose object instance, clone method, object instance, and as mentioned, we're just going to specify load children as true. Now that's it. We have now loaded that object. We've effectively spawned it in to this scene. So if what I want to do now is, we still want it to fly out into the world, so we still need to give it a shove, so to speak. But what we did previously was we manually set up the physics model and suggested, if you remember the second parameter, which was the hint for what shape we wanted it to be. We manually set up a shape and we specified simulation quality and so on. Now again, we don't necessarily have to do that because we are designing our object here in this construct scene. So I'm going to select that and I'm going to change its model to rigid dynamic and change its quality to continuous collision, which again, if you recall, was this line of code here, set simulation quality CCD. That helped to prevent the object from tunneling through walls when it was moving very quickly. Okay, so mass, that's fine for now. Actually, I need to point out something with regards to the mass that may confuse you initially. Here we can see that we've specified the base mass of 10 kilograms. In fact, that's the default. But the overall mass is 50.3 kilograms. Why is that? The reason is that by default, the mass will take into account, the final computed mass will take into account the scale that has been applied to the object. So if I scale this up and down, I'll scale that up, then we can see that the overall mass now, after it's been scaled, is 227 kilograms because I've scaled it up. If I scale it back down, you can see that the overall mass is now 12 kilograms. Now, that's very handy in cases where you want to have a lot of objects that are all different sizes, and you don't want to have to go through and select an accurate mass in each case. So say you had like one small object and you scaled it up by a factor of 10, and then you copied it again and you scaled that up by a factor of 10 again. You can just have the base mass be 10 kilograms in each case, and when you scale it, it will automatically scale it by a factor of 10 in each case, and that will be the final mass that it chooses. Now you can override that behavior with this this value here, mass scale strength. By default is 100%, which means that it will get that behavior, that scaled mass behavior. But if you just want to use the base mass in each case, then you can set that to 0%, and the overall mass will essentially be an exact copy, irrespective of how the object has been scaled. Or you can go somewhere in between. You can specify, for instance, it has a 50% influence, and it will end up with a mass between the two. For now, I'm going to want to control it directly, so I'm going to set a mass scale strength of 0%. I'll come back later on when we look at cloning in a little bit more detail at the effect that this has. But for now, I'm just going to express it manually, and we're going to say base mass is 10 kilograms. Okay, so we've specified rigid dynamic, we've specified we want continuous collision enabled, and we've set up a mass. So what that means, let me just give this a quick save, is that the only thing that's really left for us to do, we've done everything here. We've created a mesh, we've given it a material, we've set the physics model and its quality. We just need to give it a shove, basically. So we change that to projectile, and we can actually just get rid of all this now. So let me save that. So that's cut that down quite a bit. We're now basically finding the turret, which is this guy up here, based on its instance ID. Then we get the scene, load the object we're interested in, and then we give it a shot. So let's, fingers crossed it will work, let's give it a try. Okay, now at the moment that is working, our object is being spawned in, but one step that I neglected to take was to actually position it in the correct location, which was something else that we did here, first line. I actually completely forgot to do that. So projectile, set position, there we go. We still need to position it where we want it. Save, let's try that again. Hey, there we go. Let's move this out so we can see a little better. So, that's a little bit too far forwards, isn't it? Let's... we could just edit that on the fly. So let's change that to 2.5. That's better, it's closer to the end of the turret now. Okay, so we are now firing spawned projectiles. These are the projectile that we defined in our scene. Now, what's interesting about this is, remember the second parameter, the clone method, which we specified here as clone method object instance. And that guy, as mentioned, it defines whether we want to make copies or clone these guys. Now here we chose object instance, which means it's going to, every single one of these is going to be an instance of the other. Now we can demonstrate that briefly. Whilst I've still got the scene preview open, I'm going to go into the construct test scene, which you can see we're editing this scene here. We've still got the projectile selected. If I go to its collision shape, we can see here that we still have this shape. I should, if I'm careful, be able to grow this. Now if you look at these here, if you look at the projectiles as I adjust this, they all get larger as I increase the collision shape size. Now they're all referencing exactly the same object, they're all referencing this one guy, so I'm making a change to this original projectile in the other scene, and it's having an effect on every projectile here. So if I shrink this back down again, let's just fit it. There we go. So they're all back down on the floor again. Now I can change other things as well. So for instance, I can modify the material. I keep moving this thing out of the way. If you've got multiple monitors, it definitely makes juggling all the windows a little bit easier. But we should be able to modify its material. You can see that all these change red. We've got a nice blue effect going on here. Let's make them super bright. Okay, they're glowing a lot. So I've adjusted the HDR intensity there to 1000. We've got a nice bright blue electric glow on them. So we can still make changes in our construct scene whilst we're previewing. Let me just dock this back. So we've spawned, we're now spawning this object into the world dynamically without having to procedurally create the object as we go. Now not only is that more useful, it's actually much more memory efficient. In this particular case, we don't have a copy unique copy of the sphere mesh attached to each node. Every node references exactly the same mesh, the same piece of geometry, the same physical properties. Now, further to that, in terms of instancing and cloning, I would actually just like to take a brief detour just for the moment. I'm going to demonstrate what these different cloning methods mean a little more closely. Let me save that and we'll go back here. Now, in Carbon Forge, one of the most useful tools is the ability to clone an object. And the way that we do that, we can either, from the edit menu, select an object and choose clone selected. Here I've got a light source selected, but it'll work for just about anything. The alternative is to choose a transform method, and when moving, hold shift. So if I hold the shift key and I drag this light source, instead of moving it, I will actually make a copy of it. And we get this dialog pop up that allows us to specify the cloning method that we want to use, number of clones, and a name. Now if I choose copy, and I'm going to say I just want one clone, then we get what we would expect. We get a copy of the light source. And you can see here that this has an outer range of 60. If I select this and change this to 100, then when I select the original light source, you can see it still says 60 meters. That one says 100, and so on. I've made a physical copy of the object. Now, one of the other options is, if I do that again, is object instance, which we saw when we were procedurally spawning the object in. We can specify clone method. These are the same methods, object instance, data instance. So if I choose object instance, one clone is fine. Now, one thing you may notice is that these parameters, these properties in the property grid, some of them have turned red in color. And that indicates that at least one other object shares this parameter value. So, as an example, we have two light sources here. If I select the second of the two and change the outer range to 100 meters, the other one also is set to 100 meters. Now the reason for that is because in Carbon there are 3 layers to every object, or potentially three layers to every object. At the very top we have the node, the object node, which we've seen many times to this point. But you also have the object, which is the underlying thing that the node references. So in the case of a light source, this point light source, there is a top-level node which references a point light object, a physical object. So the node has the transform, the actual position and orientation, and a few other properties which you can see here that don't show up in red. So behavior script is at the node level, update rate is at the node level, name, instance ID, visibility, mass, that kind of stuff. Target method, which we'll look at a little bit later. Those are at the node level. These guys, the red guys, they're at the object level. They're one level lower down. Now what that means is when we clone a node, if we choose copy, what will happen is we'll get a new node and a new object. So it'll make a copy of both. Now when we choose object instance, what will happen is we get a copy of the node at the top level, but they both reference the same underlying object. So if we were to imagine that these were the nodes and these were the objects, then this would be the scenario that we get when we copy this light source. So we get our nodes, and under them in memory we actually get an underlying object for each, because it makes a copy of both of them. In the case of where we do object instance, there is only one object still, but we get two nodes both referencing the same single object. Now there is a third option which you saw called data instance. Now, as mentioned, there are actually 3 layers to each object, or potentially 3 layers for each object. And one object type that has 3 layers is a mesh. Now effectively, the reason for that is similar to a point light, or in fact any other object in Carbon. A mesh has a node which contains the physical transform and other per node properties. It has the object which can be instanced in exactly the same way that we saw with the point light, and that means that any properties that are common to both objects will still be shared. But the third layer is the physical data. In that case, it's the mesh data. Now, when we choose data instance, what that will do in the case of a mesh is it will make a copy of the node and a copy of the object, so we've got 2 distinct physical objects, but they both reference the same resource, the mesh itself. So the difference between object instance and data instance is may seem slim, but it is an important one. It mostly affects meshes. Again, if you're using object instance, then you will share any of the object level properties, such as in this case range and color and intensity and so on. I can actually change this to red right now, and both light sources change to red because they are instances of the same object. With data instancing, in the cases where we have an object that has a data element, such as a mesh, then object instance will do what we see here, which is, you will have 2 nodes both referencing the same single object, and therefore automatically the same piece of data, the same physical mesh. But you can optionally choose data instance, and that will duplicate. You'll have 2 nodes, 2 objects, but only 1 piece of physical data. That allows you to still customize the properties independently at the object level, but still share the mesh data. Anyway, long story short, those are the cloning methods. They're available in the editor as well as in the code for the loading method. And let's do something fun with that to demonstrate. So what I'm going to do is save this. I'm going to import an object, something, I don't know, like a crate. Yes, I do not want dummies or lights, I just want the mesh. We have a crate. So let me just fix up its material real quick. Want the normal, and we want the specular mask, and we want some specular. Want it to be very shiny. Okay, let's save that. Let's call it crate, and we will give it a rigid dynamic physics model. That's fine. Base mass. Double check the collision shape. It is fine. It's fits nicely. Okay. So what we can do is select this guy, and we'll clone him. We'll choose a cloning method of object instance. We want to share everything, that's fine. And number of clones, we're going to set to, I know, 9. Okay. And we'll get 9 additional instances, so 10 in total, of the crate. Now, if I select these, I'm actually going to clone them again in this direction. Just a few. Don't want to go too crazy. And then we'll clone them all up. Object instance, clones. 4. There's quite a lot of objects there. That'll take just a moment. There we go. Let's save that. Okay. So we have a bunch of objects that we've cloned, but because we used object instance, there is only one physical mesh. But they all share the same object properties because we chose object instance. And we'll see that in just a moment, but first I want to run into these things and let's see if we can hit them with our turrets projectiles. There we go. Too much fun. Okay, let's reset that. So, just as we saw before, when we were using object instance during spawning, in fact, let me turn on show collision shapes, which will make sure that they're always visible. If I select just one of these, just one of these collision shapes, you'll see that they all select. And if I make a change to this guy, you see they all change, just as we saw before with the construct test. Now, I'm not going to copy all those again, but what I'm going to do is I'm just going to make a copy of one of them. Now, rather than use copy, sorry, I'm going to use data instance, one clone. Okay. Now, this guy, although he shares the mesh data, because I chose data instance, remember there are 3 levels in a mesh, he shares the same data, so that's very efficient in terms of memory and instancing and so on. The object properties, which in this case, for instance, the sub-element, are unique, because I chose data instance instead of object instance. So if I add no box to this guy, I can scale this independently from these. So that's an example of where data instance differs from object instance. In this case, the object itself has unique properties, but its data is still shared. Now, there are very few object types which have a concept of a data component. Meshes really are the only main one. But hopefully that demonstrates why there's a difference at least. So let me go ahead and get rid of this. Let's turn collision shapes off. Now let me select all my crits. I'm going to move them slightly. Great. I just want to do it again. Okay, anyway, enough of the distractions. So, construct scenes, moving back to these for a moment. So we designed this object separately from the main scene, and we saw it was very successful. It loaded in just fine at runtime, and we were able to maintain an instance to it. Now, as I mentioned earlier, the third parameter to the load object node method is the load children. Now, to demonstrate that, I'm going to use a tool that we haven't used before, and that is the attach tool, which is this guy up here. Let me just redock this so we've got full screen. Okay. Now, just for the sake of it, I'm going to use another object type under Objects, Special Effects, there we go, Particle Emitter. What I'm going to do is I'm going to attach a particle emitter to this guy. so that it leaves a trail behind it, a blue trail. Let's see if we can pull that off. So particle emitters are objects just like meshes, and I'm going to select that. Now it has a default setup, which in this particular case is kind of an additive fire, which is not necessarily what we want, but let's just place it initially. Okay. Now this has a target, which I don't actually want. I'm going to get rid of that. And under placement, you'll see there's a target method. Sorry, I need to select the actual particle emitter itself. Under placement, target method, currently z-axis. I'm going to change that to disabled to get rid of the target. It's now just a freestanding non-target particle emitter. And I'm going to put that somewhere in the middle. So let's leave it outside for the moment so that I can attach it. Let's turn this off. If I select it and choose enabled, it will stop firing its particles. Now, at the moment, these two objects are physically separate. Particle emitter is there, and our sphere is here. If I move this guy, nothing happens to the particle emitter, and if I move this guy, nothing happens to the sphere. However, what I can do is I can attach the particle emitter to the sphere, or vice versa. Can have any number of attachments by clicking the attach button, clicking and holding the left mouse button on the object that I want to be the child, and then releasing it on the object that I want to be the parent. So in this case, I want to attach the particle emitter so that it's a child of this sphere here. Now, it won't look like there's anything particularly different initially, but if I go into the scene outline, we'll see that the particle emitter is indeed now a child of the sphere. If I click the sphere and move it, the particle emitter will actually follow me. If I re-enable it, you see it actually follows the sphere itself. But as a child, I can actually still select it and move it around without affecting the parent. So I'm going to do that, and we'll put it roughly in the middle. Let's go down to a top view. That's fine. So the first thing I'm going to want to do is I'm going to want to adjust the size of this guy. It's a little bit small because our particles are fairly small. I want this to have a bigger tail, so to speak. So let me select the emitter. Now there are a couple of ways to do that. Over here we've got base scale, and we've also got size, which are two independent properties. Size is how large we want the sort of size of an individual particle to be, and base scale is how much to scale that size independently on a per particle basis. Now the reason why those two properties are distinct is because, as with most of these properties, we can actually specify a range. So with the scale we can actually choose a minimum and a maximum base scale. So if we were to change the maximum to say 10, I won't do that just here because it will blow everything up, and leave the minimum at 1, that means that randomly, as particles are created, they will get a scale of anywhere between 1 and 10 to introduce random variation. Most of these properties have a similar min and max. So the linear speed, for instance, 2.5 meters a second to 3 meters a second, that's the initial speed. It will have a random variance between 2.5 and 3. Initial angular speed between minus 150 degrees a second to 150 degrees a second means these guys spin. Their mass, which doesn't apply in this particular instance. We have no mass, no properties which are being affected by mass right now. that's pretty much it for the particle simulation. In terms of emission, we can specify cone angle, inner and outer cone, emission radius. Like for instance, I could set that to the outer cone to be 179 degrees, and it would come out in a massive hemisphere. But I could also change the inner cone to 178 degrees, and now it will come out radially from that center point. So you can specify an inner and outer cone. Let's change those back. Emission radius is the radius of the base. So if I change this to 1 meter, it would actually start emitting from points 1 meter away from the center point. So you can think there are lots of little 50-degree cones scattered about up to 1 meter away from the center point. Dead zone, if I change this to 2 and change dead zone to 1.9, it should create them in a ring around that center point. So it will be dead within out to 1.9 meters, and then it has a possibility of spawning a particle. Auto unload limit, will perhaps look at that another time, but essentially auto unload limit means that the node will automatically unload itself once it's released X amount of particles. Let's change this back to 0 and 0. Burst frequency is the rate at which it will release new particles, so 60 per second is what we've got it set to here. It's also the default. Maximum particles, you can limit this, you can limit the system overall to a total maximum number of particles. So if I set this to 5, it would still try and release particles at 60 per second, but it's not going to be allowed to because of the maximum particle limit. Now that the value that you set there, if you're not going to leave it at 0, which means that it will automatically compute the maximum particles, is factored based on the lifetime of the particle, the maximum lifetime, which in this case no particle can live longer than 1 second, multiplied by the birth frequency. So if no particle can last longer than 1 second, and we're releasing 60 particles a second, then our system is never going to need to have more than 60 particles. So we could set that to 60 and be guaranteed that none of them are getting truncated. But if we wanted to guarantee that we only had a certain number of particles alive at any time, we can forcibly set that. Or we can just set it to 0 and the system will compute automatically the correct maximum number of particles. So anyway, back to what we were doing. I was adjusting the size of these things. I want a slightly larger scale, so I'm going to do 1.5 to 1.5. I don't want any variance. I'm just going to set it to roughly match this guy. It's looking pretty good. Now I can mess with the colors by using the color keys. Now these are essentially animated, it's an animation curve where the left is when the particle is born, and on the right represents when the particle dies. And I can configure these colors independently. Right now the default is just to tail off the alpha. I'm going to hide those, and what I'm going to do is I'm going to select the red, set it down here somewhere, then we'll select the green, just so you can see it. Green. Then I'm going to select the blue. We're going to, whoops, put that back. I'm going to put that, let's try there, see what that looks like. Okay, it's fairly purple. Let's play with that some more. Blue. Maybe we're going too small. Let's go much higher. The main issue here is that this texture is actually yellow, so tweaking its color is somewhat difficult. because we're using a combination of the color key that we specify here and the color of the base texture. If I modified the base texture so that it was just white, it would take all of its color from the color key. So that's something to bear in mind. Now we can change the HDR intensity and the blending method. Here, blending method is additive, that's kind of the default. But notice how it's clipping away here where it hits the block. What we can do is we can change that to soft additive. The soft variant will fade as it hits, so it's a slightly softer blend when it touches another object. That's a kind of cool effect to go with. HDR intensity, we can make that very bright, which I think I may actually do. Let's go with that. Now, because of the fact that this is firing from our turret in the sample scene, we don't actually necessarily want it to have any velocity of its own. Potentially we want to see it just that the particles stand still once they've been released. So what I'm going to do is I'm going to change the linear speed, the initial linear speed, to 0. Now this will just be a fireball, kind of like glowing away on its own. So I'm going to save that. Okay, because our projectiles are moving fairly quickly, I'm going to set the birth frequency up a fair bit and change that to 200. Let's go crazy. Okay, I'm going to save that. Okay, now let's go back to our sample scene and let's see what it looks like. So when I now fire, okay, we get a really nice kind of like railgun effect. Possibly needs a few more particles for the speed, but it's looking pretty good. It's going to bog the system down a fair bit because these emitters are not being destroyed currently. Now what I could potentially try to do is to set the the auto unload limit to, you know, something like 800, so we get 4 seconds or so of emission. That would benefit us slightly. And I could also maybe attach a light source to the projectile too, so we get kind of a light streak past. Let's give that a go. So let's change the auto unload limit to 800. We should get a few seconds of emission. Now I'm going to create a light as well, and we're going to fairly intense. Let's go out to 10. Let's give it a blue tint as well. Now again, I attach it as a child by left clicking. Oops. I just attached it to the box. Now to detach, what you need to do is select the object and then press this detach. You'll get a ding to signify that it worked. There we go. Let's just verify. Okay, so our point light is now a child of the sphere. And I'm going to position it. Let's use the top view. Let's position it in the middle. Okay, I'm fairly happy with that. Let's see how it works. Fingers crossed. We should get a light, and the particle should unload itself after a few seconds. Let's give it a go. Okay, so you can definitely see the light there streaking past. And after a few seconds, After a few seconds, you can see the particles end, and we're just left with the sphere itself. So that speeds things up somewhat. We still have a unique light source for every single one of these objects. That would need to be unloaded too. We would potentially assign a script to our projectile to handle that. Maybe it has you know, a relatively low update rate to keep things efficient, and once it's done it can disable itself or unload its own script if necessary, so that we're not constantly calling into scripts for every particle. Let's fire some more of these bad boys. Okay, so there we have a really rough, brief example of a construct scene, and as a place to design an object which we can then spawn in. It's a very powerful concept. We can see it in place. We can place whatever we want in that construct scene, and you know, we're only going to be spawning in the one object or several objects from it. You might have you might design several different types of projectiles in this scene and just pick the one you want to spawn at runtime. So essentially you have a little collection. It'll have the materials which are associated with only the things in that construct. You know, so it's a nice way to have a small collection where you can design your prefabs and see how they look together and so on. You know, without having them be in the main scene. They won't be loaded at runtime when you load that scene. They will only be loaded the moment you you spawn them. And we get to take advantage of instancing, which makes for great memory savings, and you know, allows us essentially to keep us honest with the amount of stuff we're spawning in. You know, we can cut down on the amount of geometry we have resident, and we can also share properties between them. It's a very powerful concept. Anyway, I'm going to leave construct scenes there for the moment. We'll see them return in just a little while. What I'm going to do now is move on to one of the big final components which we need to be familiar with, and that is application states. Now, I mentioned them earlier, and I mentioned them in the last video as well. Application states, let me just close this construct scene down, and let's jump, let's stay in the script for now. Application states in a lot of ways are very similar to object behaviors. Now, as we know, an object behavior allows us to hook in to the scene's processes at various different points on a per object basis. So for instance, each object has an update process that we can hook into here, and we can specify when that happens, whether that's every frame or not. We can also hook into various key events and, you know, object attachment, detachment. There are other methods. There are actually physics step methods that we can use, which I think I will actually see in just a little while. But the issue with object behaviors is they're a little bit lower level than we need when we want to provide custom behaviors for the game as a whole. Now, as I mentioned, your application will likely have various different states. So you might be in the main menu, or you might be during in gameplay at that particular moment in time, or a high score table, or any number of different states that your application might be in. You know, we need to have a way to provide logic, high-level game logic, that dictates how the game plays out. From the moment the user double-clicks on the executable or the shortcut, what happens? Do we get a splash screen? Do we go straight to a menu? Do we you know, go straight into gameplay? Those things all need to be decided by somebody. Now, we could do all this in the C++ and hard code this in, but The application state concept that Carbon supports allows us to define them either on the C++ side or as scripts. Now, Carbon Forge allows us to preview those state scripts that we develop, and I'll give you an example of that. I'm going to close this down. In fact, I'm going to close this whole thing. Let's, yes, I would like to save that. Let's start fresh. And I'm going to open the full Colony 6 world. This is the world database that is used for the full Colony 6 Carbon demo that is available for download in binary form from the software and tools page. And that has a kind of more fleshed out gameplay behavior, in the sense that, you know, it has a main menu, it has a storyline as such during gameplay, the player has objectives that they need to meet, the game has end conditions that need to be tracked, there's music to play and all sorts of stuff like that. Now, what we've seen with if I were to open up the main scene from the Colony 6 demo for a moment. Now, aside from all the crazy wireframe stuff and the navigation meshes and navigation points and so on, this should be fairly familiar to you if you've played around with any of the demos. Now, what happens when I click the preview button by default in Carbon Forge or press F5 is we get our default preview. Essentially first-person shooter style, lets me run around and view the scene as I would see it normally. But it doesn't include any of the gameplay logic that I need. There should be, you know, an orc over here shooting a turret, there should be spinning lights, should be music playing. And if I weren't making a first-person shooter and I was in fact making a space sim, then this would be completely useless, this type of preview. Now, it's worth pointing out that this, what we're seeing here, is actually an application state. When I press F5, Carbon Forge creates a default application state that is designed to be kind of like a first-person shooter walk-around. Now, we can define our own application states and provide them to Carbon Forge in much the same way that we see the default preview here in the form of a script. And to do that, let me just end this preview. If we go into the Asset Explorer, here we can see under User Assets, I've actually got the main application state scripts, which we'll look at in more detail in just a moment, but those have already been added. Now I can right-click on any of these scripts and choose Set as Preview Entry Point. It has to be an application state script, not an object behavior script, or any other type of script. It has to be an application state script, but we can mark it as our preview entry point. And we'll see what that does in just a moment. But let me open up a different scene. So to illustrate my point, if I open up this main menu backdrop scene, if you've played that demo, you should recognize this. It is the background for the main menu. Let me just position the camera to roughly where it is in the main menu. Something like that. So you should recognize this. It's basically just a scene that has two spheres in it. One big one there, and another one over there. A couple of light sources. And the sky element in this case is a simple image, which is why it doesn't move when I move the camera. Now obviously, with our default first-person style shooter application state, that is the default in Carbon Forge, when I hit F5, I'm just going to fall pretty much indefinitely to the floor, and it's of no use whatsoever. This is a menu, and there are no menu elements. It's not a first-person shooter. So what we actually have here is the application state script that is used by the actual game at runtime. And I can actually select that by right-clicking, set as preview entry point. And if I right-click again, you'll see that it's still ticked. Now, when I press F5, instead of launching the default scene preview, it launches that script, that application state script, and it will do whatever that script is designed to do. So if I press F5 now, you'll see we actually get a menu. And we get some music. In fact, let me just turn that down just a bit. So we get the music, we get the menu options. Here is our background scene here. You can see it has the sun there, the star with a nice flare and the rotating planet. And we have our menu options, which we, in theory, can click. So rather than plummeting through space endlessly, we actually get a useful preview. Now I can essentially prove that that is indeed what's happening here. If I just move this a little bit, let's move this out. In fact, let's move it a lot. Then when I hit F5, you can see we've actually modified the background scene. In fact, let's make it even more obvious by, I don't know, I don't know whether this is going to be in shot or not, but let's just add an object. And you can see that cylinder I just added is there in the menu. So let's get rid of that. Close enough. Okay, but with application state scripts, we don't actually have to have a scene open. In fact, if we do have a scene open, then when we launch, when we launch the preview, it will in fact close any scenes that we have open. So to prove that, unlike the scene preview, the default scene preview, I can close this scene and I can still press F5 and it will still launch the menu. In fact, it doesn't matter which scene I have open. I almost press exit game there to exit. But I could, for instance, I could load any scene. Let's load this prop scene, which is a construct scene that has bunches and bunches of props in it, which are actually used in the main scene. But I can still press F5 and I'll still get the menu. And we'll see why that is in just a moment. So the scene that you have open isn't important. It will reopen the scene views that you had open before, but you're not, unlike the default scene preview, you're not previewing the selected scene. You're in fact running an application state script which has complete control over everything. It will load its own scene, it will render in its own way, as we'll see in just a moment. So if I open up the main menu script, which we currently have as our preview entry point, you'll see that it is in many ways, as mentioned, similar to an object behavior script, in the sense that it has a class and its name has to match the name of the script. But in this case, it is extending the iScripted app state interface instead of iScripted object behavior. Now it has a number of default hook methods, which the framework will call at various points. The first one is this one, initialize. Whilst that's similar in many respects to onAttach, it's actually more like a constructor. It gets called once when the state is first registered with the system. A state can be reused over and over again several times. So, as an example, we might have our main menu here that we first enter when we start the game, but the player might click on New Game, go to the gameplay portion, play some of the game, return to the menu, then he might go back to the game again, play some more, then come back to the main menu again, and so on. So these states, we may actually enter and exit them several times throughout the lifetime of the application. Now the initialize is just called once when the state is first registered, when essentially things are starting up. So everybody gets a chance to initialize as soon as they have registered with the system. That's what this method is for. And here, similar to the object behavior, we are passed a reference to the C++ side state object, which we can store if we wish. We don't have to. But here we do. Next we have begin, which is more similar to onAttach than the initialize function is. Effectively, begin is called whenever we enter that state. So in the prior example that I gave, we entered the main menu a number of times throughout the application's lifetime. In each case, the begin method will be called as we enter that state. And likewise, we have an end, which is called whenever we leave that state. And again, that might happen several times, depending on how we've set things up. I'm not going to worry too much about the internals of these functions just now. The next method of importance is the update method. Generally speaking, every application state script or C++ side derived class will have one of these guys, and that is where we perform any processing on a per frame basis that we need to perform. And finally, we have a render method, which we use to render whatever we want to render. Now, by default, Carbon won't do anything. If we provide it with an application state and we don't have an update or a render method, then when we run the application, we'll get no output and nothing at all will happen. It's the application state's responsibility to decide what to do, which scene to load. During its update call, it might do some custom processing, but it will also need to let the scene that it loaded know to update. Similarly, in the render method, it will be required, as you can see here, to let the scene know to draw. Now, we might want to render the scene several times depending on what we're doing. This might be a split screen 4-player game and we want to render 4 different representations of the scene. It's up to us what we do here. Carbon will, make no assumptions about what we want to do. So that's essentially where the application state comes in. It's our way of defining what happens in our game. So in the main menu, let's just give it another run. That's way too big. Okay. So I can interact with the scene preview whether it's docked or I've undocked it, as I've done here, by left-clicking on it. It will then capture the cursor and I can interact. If I press escape, it will release the cursor and I can carry on working with, for instance, the script here. Now, here we can see that the planet in the background is rotating very slowly. I don't know whether you can see that. In the update method, you can see I actually do that here. Background planet, rotate local, 1 degree per second. Now I can actually edit that on the fly, similar to the way that I did the object behaviors. So I can change that to 20 and hit save. And you can see the planet is now rotating much more rapidly. So we can edit the application states in a similar way to our object behaviors, and so that we can, find out what we like without having to constantly restart the preview. In this case, for instance, when I hover over an item and let go, you see it fades out there. Perhaps I want that. It helps if I don't press F5. Perhaps I want that to fade a little quicker, so in the render method, I believe, we have our options, fade time 0.5, so I might want that to fade a bit quicker, so I change that to 0.2, wrong key, then you can see that fades much quicker. So rather than constantly restarting, we get the ability to edit edit the scripts in real time and see the effect. So that's definitely a dead handy feature. Okay, so as mentioned, we can have more than one application state registered in our application, and in Carbon Forge, as in the C++ side, you can only have one entry point state, in the sense that you will always start with one state and you can go from there and add other states and so on. So obviously, when we're previewing this thing, here I've just got the main menu state. Now as it stands, if I press the play demo button, it shouldn't do anything. So I'm clicking the play demo and it's not doing anything. Now the reason for that is nothing to do with the code or anything like that, but it's the fact that I launched, if I exit this preview, I launched this main menu state. Now if we go down and look at, I believe it's in the update method. There we go. So in the update method, we iterate through each of the three options, new game, video options, and exit. If the cursor is within them and the button is pressed, then in the case of the new game button, begin new game. If I go down to begin new game, then you can see that we raise an event called new game. Now at the moment, there is no there's no registration for that event. There's, as you'll see in a moment, we can register certain actions that happen when an event is raised, and an event in this instance, specifically with regards to application states, is just a string, in this case new game. But because my entry point was main menu, and you can see in the initialize function and the begin, we don't register any events. We have no concept of other states. What we actually have in here in this main.js is what is truly the entry point for the game. So if I open that up and we look at main.js, you'll see that the first thing that it does in begin, here we go, is call construct app states. And once it's done that, we'll see that in a second, it sets up some audio parameters there, and then it spawns the main menu state itself. So you can think of this like a stub state. When it begins, it does some things, and then it spawns the main menu state. So if we go and look at what construct app states does, here you can see is where it registers all of the different states. So we've got the main menu, which is main menu.js, and here you can see where it registers an event action. So here, to the main menu state, it is registering the new game action. Now because I had previously just launched the preview directly from main menu, this event had not been registered. It hadn't been registered with the application state system. But if we go in via the stub state, our top level state, we can register, as it does here, all of the different states it needs, register their events, and then select the correct one to start with. In this case, we want to start with the main menu. So here for the new game, we can see that it creates a new app state event action. The type is set to transition, and the toState ID is gameplay. Now what that basically means is that when that event is raised, it's going to transition the application to the gameplay state. Now there are a whole bunch of different things that we can do. If we head over to our manual, I'm not going to go into this in too much detail here. If I go to the app state, and then we look at register event action, we can see that we have event action type. We have a number here. We have transition, which transitions the current state to the one that you specify. Transition root is useful in cases where you've got multiple application states running. You can end the entire state hierarchy in transition over. This, again, I'm not going to go into too much detail. This should be familiar to you if you are familiar with sort of more comprehensive state machines. But if necessary, I'll follow up with more information on this as it's needed. Spawn child means we will spawn a new child state that essentially leaves the current state running, but spawns another child one that becomes the active state. So when we end that state, we will return back to the parent state without unloading it or ending it. End state ends the current state. End root ends the root level. If we've spawned children, we can immediately end the root and clean up, basically. Pass up allows us to pass the event up to our immediate parent. Pass down allows us to pass it down to our immediate child. Some of this will become clearer as we progress through here, but here we're just using transition. So when the new game event is raised, we will transition to gameplay. Here we also register an exit event, which we saw end root. Here, when that event is raised, it triggers the end root action, which effectively just ends all states, ends all running states, and the state manager will effectively exit at that point, and therefore the application will exit because it's idle. We'll skip over the in-game menu. Main gameplay. This is the gameplay state here. We create a new app state, the gameplay state, the state ID, and then the script that we want to associate. So here's the gameplay state, which is the one that we transition to when the event new game is raised. So that's registered. Similarly, if we want to exit immediately, we have an end root event associated with the exit identifier. We have a restart event, which will transition back to itself. And what that'll do is it will effectively end and begin itself when we transition to ourselves. Pause game spawns a child, in this case in-game menu, and as the flags it asks for the parent to be suspended. So when the pause event is raised, we spawn a child state, which in this case is in-game menu. Obviously it's going to bring up the in-game menu in that case, while suspending the parent, so that effectively pauses the game. Jump back very quickly to in-game menu. You'll see that it has a resume, which ends the current state, which is the in-game menu. Now if you remember, we had spawn child and suspend parent there. So when we end the current state, it will pop back up the state stack and resume this guy here, the gameplay state. Restart. That, if we raise it, we just want to pass it up to our parent state, which is the gameplay state. And for the same is true of exit. We pass that up, which means that the exit will be down here. Exit will be triggered for the parent state. So that's the whole structure of the application. We first enter the main menu. They can raise the new game event by clicking on new game, which transitions to gameplay. Gameplay can exit, restart, pause. The in-game menu can pass those messages up or resume if it needs to, and the game we can return back to the menu and exit at any time. So that's the whole hierarchy in a nutshell. And this main stub, you can see it's relatively simple. We just, as mentioned, construct those app states and then spawn a child state. We have a little handler in here to exit if escape is pressed. But other than that, it's pretty straightforward. So with that said, if instead of the main menu we set that stub as our entry point, so we can see that main menu is no longer selected. Then when I hit F5, we will get our menu as before, but when I click play demo and it fires the new game event, just to remind you, so it calls begin new game. There we go. So it raises the new game event, which, if you recall, does a transition to a new state. Then now when I click this, because I'm through that stub, it will actually transition to the new state. If we just wait just a moment for the game to load.
Alright, listen up. We've lost the colony and we're
Here we're in our actual game. We're able to preview this.
Military personnel starts in a few minutes. But before you go, you're gonna leave them a little something to remember. Your armor will automatically regenerate, but it's slow. Recharge stations like this get the job done much faster. Your final orders are to infiltrate the facility and deactivate the primary generator's cooling supply. Alright, you're in. The corridor on your left leads to the coolant pump control room. You should be able to shut things down from there. Let's get moving.
Sorry, I ran out of ammo in my rifle. My problem is I know where all of the enemies are in this scene, so probably a little bit cheap.
That turret's gonna cut you to ribbons. Alright, head back the other way, go straight past the elevator, and we'll take the service tunnels instead.
So we can preview pretty much our entire game in our main application. When we actually publish this thing, that will be the main stub state that we most likely use as well. So, you know, we can pretty much do anything in Carbon Forge that we could do in our main published environment. The main advantage that we get is that we can edit some of the scripts as we go, so that we can, so that we don't have to constantly restart things, and we can play around with them and see how things work. So, as mentioned, I'm not going to go into a huge amount of detail about what's going on in all of these scripts, but as a rough introduction to a more fully fleshed out sort of application state, hopefully it demonstrates what these things are for. They handle the really high level stuff. If I go into gameplay, see, we've got things like screen messages to display things on the screen. We've got debug handling, whether we're showing dust coming from light sources. We've got events for, let me just find one. We've got triggers for current game sequences, like has the player hit the elevator yet? If we do play a sound and show a message, that kind of thing. Those are things that I guess to a certain extent we could put some of them in behaviors, and we do. These are top level overriding sort of application level logic, if you like, that is best kept separate from object behaviors because it's higher level than that. So, with that in mind, let's start to build one and see where we go. So again, I'm going to start. I don't want to save any of that. So let's go back into our sample world. Let's make sure everything is still working. There we go. Okay, so the first thing we need to do when we're creating our own application state And I'm just going to create one here. I'm not going to, I'm not going to create menus or anything like that. We're just going to create a main gameplay state. I'm going to, first and foremost, I'm going to create a new folder. Okay, then the scripts. Create a new script, and I'm going to call it sample state.js. Okay, so let's open this guy up. As we saw, similar to our behavior scripts, we need a class. We need to call it the same thing as the file, but this time scripted app state. Now we could have an initialize method, which I'm going to provide one. App state. I'm going to cache the reference to the C++ side app state object here. Private. Helps if I spell things correctly. Okay. Now we can return false from this if we want the registration to fail, but I'm not going to do that here. And what we also want is a begin method, which also returns a Boolean indicating whether we can transition to this state or not. If you return false, then the state manager won't transition to this state when requested. So if something failed, or you just, you don't need to transition to this state, then you can return false. Again, we're just going to return true here for the moment. We also have an end. An end must always succeed, so it has no return type. We have an update method and a render method. So let's just double check that we've got everything correct. I believe so. So again, we want to set this as our entry point. Now if I hit, let me just save. If I hit F5, our preview starts, we get no errors, but we also get no output. Let's drag this off. Which, based on what I mentioned earlier, should hopefully make some sense. Our application state currently doesn't indicate that it wants to do anything, so nothing happens. Our render method is empty. We don't necessarily always need something in an update method, but we do at least need something in our render method for anything to actually happen. So let's end that preview and go back to our code. So the first thing, if you recall, it is the application state's responsibility to decide what happens when we enter the state. And that includes things like choosing which scene to load. If it even wants to load a scene, it might not. But here we actually want to load in our scene. And what I'm effectively doing here, to a certain extent, is recreating what the default Carbon Forge scene preview state does for us. So what I effectively want to do is to load in a scene, and for the moment, just walk around it in a similar way. So, as mentioned, the first thing we need to do is to load a scene. Now, to do that, we need to get access to the world database. You can see here, establish connection with world database, sampleworld.cwm. Now that world contains multiple scenes, so he's the guy we need to ask when we want to load a scene. And similar to our input driver and render driver and timer that we saw in earlier scripts, we can get that from the system using get app world You know, we would use get app input driver for the input driver singleton and so on. And let's go to our manual, and we'll go to CG World. And you should see somewhere, let's do it alphabetically, load scene. There we go. We have a load scene method which accepts a scene ID. Now if we go back to our sample scene, our World Explorer, click sample scene, we can see it has a scene ID of 1. So that's the guy we want. Now I want to store that because I want to be able to reference it later. So mScene equals world load scene and then the scene ID that we want to load. So at that point, assuming it's successful, I'm going to skip any kind of error handling here, but assuming that's successful, then our scene should now be resident and we have a reference to it in mScene. Now, the next thing that I need to do is to be able to render the scene from the point of view of some camera. Now there are a couple of ways to do that. I could create a camera in the scene, or I could create a camera dynamically in code here, as we saw in our other examples. We were creating you know, our sphere objects and so on. But I've actually pre-prepared a script which is a cut down version. If I go into scripts, here, player.js, I'm going to copy that into my scripts directory. I've pre-prepared a script called player.js, which if I load that in here, add existing item, is a cut down version of the controller that Carbon Forge uses, and is also used in a number of the samples provided along with the SDK. It's relatively straightforward. It creates, you can see here, it creates its own camera. It handles things like head bob and that kind of thing. So I've pre-prepared that. I'm just going to use that in this particular example. Now what we need to do is we actually need an object to which we can attach this script. So we need to return to our create object node function, which is a member of the scene. I think we want this one. We need to specify the type identifier and whether or not it's an internal node, which will always be the case, so we just set that to true. Create object node, it's always internal. This, we don't want it to do anything special, we just want a dummy frame essentially. So we're going to create a dummy object that's one of these guys, which does nothing essentially. It is just a transform in our world, but we can attach behaviors to it, so that's the one we're going to use. And we don't care about a name. The third parameter was auto-assign name, so I'm going to set that to false. I'm going to want to store him as well. Private object node. I'm going to call this player, mPlayer node. Okay, and we're going to want to store that mPlayer node. Now I need to associate this script with this node. So if we go and look at CG object node, we want to assign the behavior script, and to do that we use one of these two methods. Add behavior, which accepts an object behavior, a C++ side object behavior type, or we can specify just the script, in this particular case, a string that represents the script file that we want to load. So that's the one I'm going to use. Player node, add behavior. Now it's in the scripts directory. Indeed. So it's in the scripts directory, and that's it. Player.js. Now add behavior returns an integer which represents the index of the behavior. Now the reason why it returns an index is because technically speaking object nodes can have more than one behavior that will execute in series, and we can get those with get behavior and get behavior count. This index can be specified directly to get behavior there. But at the moment we don't actually need to do anything with the behavior, so that should be just about it. We're just going to add the behavior there. Now in the end method, bearing in mind that we may enter this application state a number of times, it's best to clean up after ourselves. We don't want the scene that we've loaded to remain resident at all times, even once we've moved off into a different state, so we should clean up after ourselves here. I'm going to actually explicitly unload the scene if one was loaded. Okay, I'm just going to clear the player node just so I know it's been released. Okay, in the update method, generally speaking, we will primarily want to pass on the update message through to any scene that we've loaded. We can take additional action, but in this particular instance, we only want to just pass the message straight through to the scene if we have a scene, if the scene was successfully loaded. Now rendering I'm going to leave just for the moment. I'm going to save that and give it a run. Okay, no errors. In theory the scene loaded. We won't know for sure at the moment because we're not rendering any output. But in theory the scene loaded, and when we end we should go back to the scene views that we had open. Okay, so what about rendering? Well, in Carbon, in order to render a scene, you need access to what is called a render view. You can think of a render view as being a viewport of sorts, but it's actually a collection of the necessary render targets that we're going to need in order to render our frame using deferred rendering and high dynamic range lighting and so on. There are actually a number of render targets that go into that, the G buffers and so on. And a render view takes care of managing all of the needed targets for each thing that we want to render. So for instance, if we wanted two-player split screen, we would create two render views and we would render to each of them independently. And that would take care of holding on to all of the render targets of the necessary sizes for each of the two independent views. Here we're only interested in one output, so we just want one render view. We have to create that manually, and to do that we're going to need to store a reference to it. Now to create the render view, we do that via the render driver. Create render view. Got a couple of choices. So we'll use this one. This is the fully fledged one. Now, as mentioned, you can create multiple render views and output to them. When you present the render views, they will be drawn to relevant locations on the screen or in the main frame buffer. And we describe the region of the screen that we want to use through these parameters. There are two main choices. If we look at the scale mode here, we can choose absolute positioning or relative positioning. When we choose absolute positioning, then this third parameter, which is a rectangle, that describes the position in pixels, effectively, that the render view occupies. So if we chose absolute and we chose to specify to our rectangle, which has these attributes left, top, right and bottom, we can specify 10 for left, 100 for right, 10 pixels for top and 100 pixels for bottom. That would occupy a 90 pixel by 90 pixel region in the upper left hand corner of our screen. When you choose relative, the rectangle that you specify is in the values are all in the 0 to 1 range, and the size and position of the render view will always be relative to the frame buffer itself, the size of the frame buffer, and the position within it. So they're essentially more like texture coordinates in that case. So if you wanted to play a split screen, you might choose, if they were side by side, you might choose a left of 0 and a right of 0.5 for player 1, and for player 2's view you would use a rectangle of 0.5 for left and 1.0 for right. Again, here we just want one view, so first things first, we need the render driver itself, which we get with get app render driver. And then we call its create scene view method, create render view method rather, and again, so its name, we want a useful name, largely for debug purposes, but it also can be used to identify when profiling. Create render view, sample view, that's fine. We want a scale mode, we're going to choose absolute, we just want a full screen view. Scale mode, relative, and then we want a rectangle, a full size rectangle. It is a floating point rectangle, so it's rect F rather than just rect. Again, you can see that here, but the CG prefix is omitted. We need that symbol there. That should be it. We've created our render view. We'll also want to release it again when we're done. And to do that, as with all references, we can destroy them immediately by calling delete reference. There is also add reference and remove reference, but delete reference will just immediately destroy it, which is what we want here. And I'm going to empty out the reference. Okay, so we should, in theory, let's save that, have a render view created on begin and destroyed on end, just to release the memory that it's maintaining. So when we render then, how do we render to our scene view? Well, it's pretty straightforward. If we take a look at the render view, we'll see that it has a begin method and an end method, and we can optionally present it immediately when we end, or we can call the present method directly. It's really as simple as that. Here we do if scene view.begin, so if it successfully began rendering to the scene view, then we can do whatever action we need in order to render. Here we just want the scene to render itself, so we just do scene render, and when we're done, we want to end rendering to the scene view. Right, that should be it. Let's save that and give it a test run. And we have some errors, and that's because I'm using render view somewhere right there, and probably a great many of you were screaming at me as I wrote that. I apologize. We've still got no output just yet. Okay, now there's actually one more thing that we need to do, which is fairly critical. Right now, we've created our scene view, we've loaded our scene, and we've created a player object. We're also rendering and updating, so we're almost there. The last thing we need to do is to select the camera that we want to use when we render. Now, if you recall, I have this player script, this simple player.gs script here, and he creates the camera itself. So here, mCamera. So the big question is, how do we get the camera from that guy in order to assign it to our scene so that we can render? Now, this player.gs script, he actually has a number of methods, here public methods, one of which is called getCamera. Now this isn't an object behavior method, this is a completely custom method, which in C++, you know, we would expect to be able to call. It's not a method that is hooking into anything in the engine, it's just something which I've declared in the player script, and then obviously in the definition I just return the camera. So how do I actually call that from here? Now if you remember at the start, I mentioned that one of the things that I wanted to discuss was communication between scripts, how they talk to one another. In our earlier scripts, everything was largely self-contained, and we didn't have to worry about any of that kind of stuff. You know, the Viper would just fire from its turret all within the same script. But as you move forwards, you're going to need to have scripts communicate with one another, call each other's methods, and so on. Now, I mentioned earlier, and it was actually in error, but I mentioned earlier that I'm not going to need the index from this guy because I'm not going to need the behavior. That's actually not true, because in this particular instance I do want to call one of its methods. So I'm actually going to get that behavior index. So I'm going to get that back just so that I have it. In this case it's guaranteed to be 0, but to do it the correct way I'm going to retrieve and store that index. Now, as mentioned, I need to call this getCamera method on a script which is assigned to a random node that I've just created. So how do I get access to that? Well, the first thing that we need to do is we need to make this script, our sample state script, aware of the declaration of the player. It needs to understand that there is such a class as the player class, this class here. Right now, as it stands, it doesn't know it exists. We couldn't cast anything to that type. It needs to be aware of the declaration of the type. Now, in exactly the same way as we would in C++, when we include a header for a class that we've declared elsewhere, we do the same here. We actually use the include directive. There are two choices actually. You can either use the include directive, or you can use include once, which is a special version in Carbon. Now, when you just use the regular include directive, you have to start being concerned about adding include guards, or pragma once in C++, to make sure that the same header isn't, or the same declaration isn't included more than once. Here we can just use include once, and that will guarantee that if a script hasn't been loaded before, it will be loaded. If it has been loaded before, then it will be ignored. So here, that's what we want to do. We want to include the player script, which we created, so that our sample state class is aware of it. Now, there is one other change that needs to be made in order for this to work. And if I jump back to player.js, you'll notice that prefix to the class is a keyword there called shared. And the reason that exists is to inform AngelScript that this declaration is going to be shared by more than one script object. It's effectively a way to say, just compile this script once, and for everybody else who asks for it or uses it, just make sure that it's only the declaration that you're giving to them. That way, you're not going to duplicate all of the code, the compiled code, into every script in your engine or in your game. Instead, even though that would technically work, here, in order to reduce the memory footprint, we mark it as shared to indicate that we are going to share it with potentially many different scripts in our game. So we mark it as shared to ensure that happens. Now, the knock-on effect of that is that in AngelScript, in order to use a shared class, that class must also be shared. So if I don't change this class declaration, our main sample state, our top-level application state, if I don't modify this to include the shared keyword, I won't be able to use the shared declaration of our player. So I prefix the shared keyword there, and I should now be able to use shared types, such as the player. So it's now aware of the declaration of the player object. If you're familiar with C++, that should be familiar to you. Excuse me. What I need to do now is actually get the instance of the player in question. Now we know we've just assigned that behavior to the player node that we created here. That's just a dummy object. But we need to get that now. So as mentioned, the behavior index tells us where that script, that behavior was placed, which behavior it was that we added. As mentioned, that's going to be the first one here, so behavior index will just be 0. But we'll use it anyway, just to be safe. So what we need to do, I'm going to store a reference to the player. We have a reference to the player node, but here I'm actually going to store a reference to the player itself. Now notice I'm using the player type, which we've declared here in player.js. So I'm not storing the node or the behavior. I'm actually going to get a reference to the physical player class. And to do that, so to my player variable, I want to get from the player node the scripted behavior object that is assigned to the index. In this case, 0, but whatever index was returned from add behavior. Now this is actually going to return an object of the type iScripted object behavior, so the base class for the player. So we need to cast that to the correct type, player in this case. So there we have a reference to the actual player instance. It's been cast to the correct type, we have access to the type, and we are entitled to use it because we have marked ourselves as shared. So we should now have the player. And finally, we can call its custom methods now. Get camera, get controller, shake camera, teleport to. In this case, we just want the camera. So assign camera. Let's put some comments in here. Create player, load scene, create scene output view. So assign the camera we want to use, and to do that we use the scenes set active camera method and player get camera. Fingers crossed, that should be it. Now when we run this, we should see our scene view output to the preview window. So let's give it a run, and there we have it. Okay, so Although it may seem, again, a little bit daunting initially, the steps are basically the same each time. Create a output view, load a scene, create a camera somehow, however you're doing that. Here I'm using this custom player script. Set the camera to the scene, the camera you want to use. Update the scene, render the scene. Now, here we can see that our scene is now rendering. I can't yet navigate around it, and the reason for that is, you may have noticed that when I click on it, I left click to get focus, I actually have a cursor, which is the default behavior for Carbon. Carbon always starts in what it calls cursor handler mode, and we can manipulate that. There are actually two choices. There are two different modes. The one we want is actually direct mode, and we can manipulate that through the input driver. So we don't want the cursor, we want to directly control. Input driver. Again, get app input driver, just as we saw before. Input driver. Now this is called set mouse mode, I believe. Set mouse mode. Here it is. And it accepts an enumeration, which is either direct or cursor. So mouse handler mode. Input driver.set mouse mode. Mouse handler mode direct. That way it'll capture our input and pass it along rather than using a cursor. So let's run that again. Now, one other thing that I realise I've forgotten is that we've added a behaviour, but he's not currently being allowed to participate in the update process. So we need to set his update rate, just as we saw again when we were firing our projectiles originally, when they were created. Set update rate. Update rate always, we want him to execute every frame. There we go. We have movement. Okay. So here we've ended up simulating roughly what the Carbon Forge scene preview does, and we should be able to still, our object behavior still function. So even though this is running in Carbon Forge, what we've effectively done is build an entire application state. This is something that when we publish this thing and we have our C++ side version, or our compiled executable, we've now built pretty much the whole game here in what in a way that is required to in this case emulate what Carbon Forge does by default with the preview scene. But we're actually going to do something slightly different in this particular instance. What I'm going to do is just something a little bit more interesting than that. What I want to do is I want to be able to move this vehicle around. I want to attach a camera to it and drive it around. I'm not going to do any kind of fancy physics or anything like that. I'm going to do a really kind of cheesy manipulation, if you like. So first thing I'm going to do is let's open this group. I'm going to just turn off the collision on these individual objects and close the group again. I'm going to rigid static, actually no, rigid dynamic, collision shape. My top level Viper, I'm going to assign a basic collision shape, which is just sort of low down. I'm not going to do anything crazy with it. Let me delete this one. Okay, and so he's got a collision shape now. What I'm going to do is I'm going to make him super heavy, so I'm going to make him something like 1,000 kilograms. Okay, then, so what I want to do effectively is to, when I press the cursor keys, to have this drive around, but I want to view things from up here on the turret. So the first thing that I need to do is to create a camera. So under objects, under helper objects, you can see I've selected camera there. Now, okay, let me just create it over here initially. So I've created a new camera object, which is currently over here. And we have the defaults here, field of view. I'm going to bump that up to 75 degrees. Those values are fine. I'm going to put it on top of the turret. Now I'm not going to attach it to the turret itself, or am I? Yeah, let's attach it to the turret. Okay, so in order to do that, I need to open this group so that I have access to the turret. Then, using the attach tool, I left click on the camera and then release it on the turret, and that should be attached to the turret itself. I'm going to edit this ever so slightly and move it down. We can see by these lines the kind of what we're going to be able to see, more or less. So that looks good to me. Okay, so let's test that first of all. What I'm going to do is the player class, which we just assigned and did all that work with, I'm actually going to get rid of that for the moment. And instead, I'm going to retrieve this camera, which has the ID 572, from the scene. Get, I think it's get, you'd think I would know this by now. I believe it's get object node by ID. Let's find out. Get object node. Yes, get object node by ID. So we can get that camera. I could have done it using the instance ID and finding it using the find method. But this works too. Either way, I would have had to find the Viper model. So I've got the camera. Don't need any of this stuff right now. We just want to associate that camera with the scene. So if we, okay, I've got an error, mPlayer node not defined. I still have a reference to it. Okay. Okay, so you can see that I'm actually on top of the turret now. I'm a little bit off center. I'll fix that in a moment. Now hopefully I should, if I get focus, I should, there we go, I should be able to move the turret with the N and M keys from our prior script. and I can still fire my projectiles. As before. Okay, that's good. I can't move the vehicle yet, so let's move on to that. So we need to modify the Viper behavior for this. Now we're going to, what I'm also going to do actually is I'm going to make the turret its own class, so we can see another example of communication between scripts. And to do that, let's go back to our scene, and I'm going to associate with this, I'm going to create a new class called a new script called turret.js. Now rather than doing everything in line in the one Viper script, I'm going to split it up and have the turret handle its own existence, so to speak. I mean, it's one thing here to, you know, have our vehicle script, you know, trigger the firing behaviors and that kind of thing. But you know, what happens if our turret has, you know, two different types of, like, it might be a flamethrower and it might be, you know, or it has projectiles, or perhaps it needs to track ammunition or that kind of thing. You know, having everything in the one class is not always ideal. So here, let's go ahead and create our new turret class. In fact, what I'm going to do is I'm going to copy the entirety of the Viper class, paste it over here in turret. Turret. So most of those behaviors are the same. We're not going to have an update method, I don't believe. What we're going to have instead is a custom method, one which we've just defined, called rotate. Let's have rotate. Let's keep them separate because the turret might want to do, you know, might want to manage its own speed, or there might be damage, which means it can't move left, and so on. So rotate left. We need this guy. I'm going to create another method called rotate right. We need to change that from turret to mnode. We are now managing our own existence in that regard. But what we do need to know is the time delta. So that will have to be passed through. We also want a rotate right. And for this guy, we're just going to have a method called fire. We're just going to fire our projectile. So again, we need to change these references to turret. And they're just now our own local node. But again, in order to call these custom methods, these three below, these are our callback methods. In order to call these, we're going to need to reference them. So this has to be shared, as we saw with our player. Our Viper also now needs to be shared. And it also needs to include the turret class. Okay, now what we should be able to do is we don't need to retrieve that here, but what I'm going to do is similar to what we saw before. I'm going to store a reference to it, and we'll grab that during the attach process. We know it just has one behavior, so turret equals get scripted object behavior, which was the method which we saw before to get the I scripted object behavior base type. I need to cast that to our custom turret type, and that should be it. We should have that stored. I'll just trash the reference here just to keep things neat and tidy. I saved it there by mistake. Obviously I'm going to have errors. So here, rather than rotating rotating the object node, I'm just going to call the turret's rotate left method. And when they press M, I'm going to rotate right. And in here, this can all go now. I'm going to, when you press B, I'm just going to call the fire method. So we can now call the methods in theory. Have we got any errors? We do. No conversion from constant to turret available. Oh, I see why. I'm calling the wrong function. There we go. Get scripted behavior. Okay, so that should be it. We've now moved the turret specific logic into its own turret class, which we should, in theory, be able to just trigger now. That'll allow us to customize how the turret works without having to, if we had a few different vehicles that each had turrets, we wouldn't necessarily have to embed the turret's logic directly in the vehicle script. So that's a handy way, again, we can communicate with other script classes. So I'm going to fix this camera slightly. As mentioned, it's slightly off to the right. Do this from the top view, it'll be a little bit easier. There we go, that's more or less in the center, close enough. Okay, let's run. Now, do we have a working turret? We do. Okay, I'm having too much fun with that. So now we've separated that out into a separate turret class. As mentioned, I want to have the Viper actually move. Now, I'm not going to do any physics, as I said. I'm going to be extremely lazy in this particular instance, and just for the sake of brevity, we will move it manually. And the way that I'm going to do that is I'm going to have a variable here. I'm going to call speed. So we've already associated. If I go to the top level Viper, we already have a collision shape for this guy, and we've already set him up as rigid dynamic, and we're using 1,000 kilograms for his mass. Save. So he is a physics object. He will be able to interact with the scene. Now, what I'm going to do is introduce a couple of additional object behavior methods which you might find handy, and they are the on pre-physics step and on post-physics step. Now, these methods are used, they're very similar to the onUpdate method, but they are tied into the physics processes. They run on the main physics engine's time. And essentially, for anybody who registers these methods, the physics engine will call the pre-physics step method before it runs the current iteration that it's about to process of the physics world, the physics simulation, and it will call on post-physics step once it's done. The interesting thing about that, although it's not necessarily always the best place to do all of your processing, it allows us to manipulate the physics body in certain ways and get feedback once the simulation has run that we couldn't otherwise get from a single update process. So here in the pre-physics step, I'm going to, so we've got our variable called speed, and on attach, let's just default that to 0. So in the pre-physics step, I'm going to compute a usable current speed. and I'm going to use the input driver to get the cursor key inputs. So if the up key is pressed, I'm going to increment the speed by, I'm going to accelerate by 50 meters per second. Per second, I guess. If the down key is pressed, I'm going to slow down. Now this is a really cheesy, hacky implementation, but it will get us what we kind of need as rapidly as possible for the sake of this very long video at this point. Now if we're not holding the down key, we're just going to slow down. I'm just going to slow down normally. In fact, what we want to do is, if we're not pressing any key, so not pressing up or down, then if we're currently going backwards, I guess add some speed. Otherwise, if we're currently going forwards, remove some speed. This code won't win any awards, I guarantee it. We also want to cap the speed so we can't go too fast. M speed is less than, let's say, -10. M speed equals -10. Else, if M speed is greater than 10, M speed equals 10. So that should just about do it for the speed calculation. Very rudimentary. It's a terribly hacky way to do it, but it should work for these purposes. Then what I want to do is I want to set the velocity of our Viper object to match that speed based on its current orientation just before the physics step, simulation step runs, which is why we're doing this in on pre-physics step. So I'm going to set the velocity of our object to match the current z-axis direction, or z-axis direction, multiplied by the speed that we've calculated. And that should get us the speed that we want, or the velocity that we want. I'm also going to... In fact, let's just do that for now. Now, if we run into something, if our object hits something during the simulation step that's happened after the pre-physics step and before the post-physics step, then our speed might have been reduced to 0. So I'm actually going to get the speed back here by computing the length of the node's final velocity after the simulation step had run. Now, the length will always be positive irrespective of the velocity direction, so what I'm also going to do is again, another bit of a cheesy hack, but if the velocity is in the opposite direction than we're facing, then we're reversing. Or something along those lines. Let's see how this works. Error on line 86. Yes. If the dot product is less than 0, that's better. Okay. Let's give it a run. Now we should be able to, with the cursor keys, move forwards and backwards, which we can. And we have a little bit of acceleration and deceleration. I press back and let go. I press forwards and let go. And I can still move my turrets. Let's try running straight into this thing head first. There we go. Okay. This tomfoolery. Now I can edit these. Let's just change these max speeds to something stupid while it's running, just to test it. Oh. So the physics process is still running, and when I hit objects, I'm still mostly handling normally, except for I'm sitting on a box right now. There we go. This thing weighs 1,000 kilograms, so when it's standing on a box, it's not much fun. Okay, so let me cancel that, and we'll go back to sensible speed. And I'm going to add now I know that works, I'm going to handle the rotation. So if the left key is pressed, we're going to want to rotate to the left by some amount, but we don't always do that. We don't always want to rotate because the vehicle might not be moving at all at that point, so we should modulate it by the current speed, and obviously we need to make it frame rate independent as well, so we'll see if this works. We'll do the same for right. Save. Run. Right, can we turn when we're stood still? We can't. When we move. We can, it's a little bit severe. I don't know why it ended that. Let's change this to 7. That's better. So we can now move this thing around. Like I said, nothing too fancy. Let's restart that, but let's get a bit of a bigger view on this thing. So I'm just going to have to clear all these up, and it's not going to be me. In hindsight, I could have chosen better keys for the turret. Okay, I'm fairly happy with how that's looking. So, essentially, to cut a long story short, what we've done is we've built a custom application state that we can preview in Carbon Forge. That is not at all like a first-person shooter. Obviously, we are now attached to the top of a vehicle that is moving through the world when we press the cursor keys, and we can fire our projectiles out that we're spawning in from a construct scene with all its particles and light sources flying everywhere. So we're not always restricted to just what the default preview is when we want to design how our game's going to function, and we don't have to resort to the C++ either. We can do it all directly in the editor itself. So, given the ridiculous length of this video to this point, I think I'm going to end it there. Up to this point, we've seen some of the more advanced features, let's say, of Carbon and Carbon Forge for actually starting to put together games. I think that this may creep into a third part, probably a smaller part, where actually take the application state a little bit further and build something a little bit fun from it. at the moment we have our vehicle moving around, and that's pretty fun in and of itself, don't get me wrong, but we need some objectives. We need to be able to actually win at this game and have something to do other than fire into a whole bunch of crates. But we'll save that for next time. For now, I hope you found something useful in this, and that you've at least enjoyed some of it. Until next time, take care.